Hi everybody, in this video we're going to go over greatest common factor and least common multiple. So when are you going to be using this? Greatest common factor and least common multiple are found in the grade 6 Common Core standards and in Georgia's math standards. So in the Common Core standards, we see that in grade 6 students are expected to be able to find the greatest common factor of two whole numbers less than or equal to 100. They're also expected to be able to find the least common multiple of two whole numbers less than or equal to 12. And then they're also expected to be able to use the distributive property to express a sum of two whole numbers, 1 to 100, with a common factor as a multiple of a sum of two whole numbers with no common factor. Now that sounds complicated, but let me just show you what that's saying. They're expecting them to be able to factor out a common factor. So for example, if you have like 5x plus 10, right, so that is currently written as the sum of two numbers. I've got an x in mine, but we've got two whole numbers, 5 and 10. They're expecting those students to be able to factor out that common factor of 5, which would leave us with x plus 2 inside the parentheses. All right, and then in Georgia's math standards, we see that students are expected to be able to determine the greatest common factor and least common multiple using a variety of strategies to make sense of applicable problems. All right, so they're expecting students to not only be able to find the GCF and the LCM, but also to do this using different strategies, and they should be able to do this on word problems. All right, so let's talk about the greatest common factor. This is also sometimes called the greatest common divisor. So those two phrases can be used interchangeably. If you see greatest common divisor, just know that's the exact same thing as greatest common factor. I will use the terms interchangeably. All right, so the greatest common factor in the most simple terms, it is the largest number that can go into two or more numbers without leaving a remainder. Right, so they go in perfectly. Right, so it's the largest number that can be, that is goes into or is a divisor of two or more numbers without leaving a remainder. Another way to say this is it is the largest factor shared by two or more numbers. So remember, factors, those are how we describe the pieces when we are multiplying numbers. So we're referring to multiplication here. All right, so there are many methods for finding the greatest common divisor or greatest common factor. You can use Cuisenaire rods. You can use what's called the intersection of sets method. You can use the prime factorization method or the Euclidean algorithm. I will tell you that for our test, I will be focusing on these top three methods, with more emphasis being put on the Cuisenaire rods and the prime factorization. Right, so intersection of sets is fine. I just don't find it to be particularly more useful than the Cuisenaire rods or the prime factorization method. Now I'm going to show you how to use the prime factorization method to find the greatest common factor of 192 and 360. Right, so we're going to need to create factor trees for both numbers. All right, so I'm going to go to the next page, give myself a little bit more room to create these factor trees. All right, so let's start with 192. My first instinct here was to divide by 2 because I see that it is divisible by 2 since it ends in an even number. But then whenever I considered the divisibility test for 3, so I added up the digits of my number. That was 1 plus 9 is 10, plus 2 is 12. I thought, okay, well, it's also divisible by 3, so I'm going to go with 3. So I broke 192 down into 3 times 64. All right, so 192 is 3 times 64. 3 is prime, so we go ahead and circle it. For For 64, I went ahead and broke that down into 8 times 8. If you broke it down a different way, that is totally fine. Then I went ahead and worked on both of my 8s. All right, so 8 can be broken down into 2 times 4. 2 is prime, so we go ahead and circle it. 4 can be broken down further into 2 times 2. Both of those 2's are prime, so we circle those. All right, so then go ahead and do the same to our second 8, breaking it up into 2 times 4. 2 is prime, so circle it. 4 can be broken down into 2 times 2. Both of those 2's are prime, so we circle them. All right, so next we're going to work on 360. All right, so since I knew that this ended in 0, I knew that it was divisible by 10, so I broke that down into 36 times 10. 36 could then be broken down into 6 times 6. Those are not prime. We need to break those down further. So the 6's can be broken down into 3 times 2. 3 and 2 are both prime, so we'll go ahead and circle those. The other 6 gets broken down into 3 times 2. Those are both prime, so go ahead and circle those. And then 10 gets broken down into, or broken up into 2 times 5. 2 and 5 are both prime, so we'll circle those. All right, so from 192, let's count up our factors. All right, so our prime factors. We've got 2, 2, 2, 2, 2, 2. We've got 1, 2, 3, 4, 5, 6 2's and 1 3. And for 360, we've got 1, 2, 3 2's, 2 3's, and 1 5. All right, so we can express those as 2 to the 6 times 3 for 192, and then 2 to the 3rd times 3 squared times 5 for 360. All right, so when you are using the prime factorization method to find the greatest common factor, you look at your prime factorizations of your number, you figure out the factors that they have in common. All right, so for our numbers, for our prime factorizations, we have a 2 in common and a 3 in common. All right, if they share more than one of the same factor, write those down. Then multiply the factors they have in common. All right, so look at the 2. How many 2's do they have in common? They both have 3 2's. And how many 3's do they have in common? They have 1 3 in common. All right, so we're looking at the exponents there to figure out how many 2's do they have in common? How many 3's do they have in common? All right, so now we take the common factors and we bring them down. So our greatest common factor is 2 to the 3rd times 3. 2 to the 3rd is 8. 8 times 3 is 24. So our greatest common factor of 192 and 360 is 24. This is my favorite method for finding the greatest common factor. I think it's the easiest to use, but you can use whatever method that you prefer. Now I'm going to show you how you can use Cuisenaire rods to find the greatest common factor of two smaller numbers. So this is a technique that you could use in your own classroom. First, let's just remind ourselves of what the Cuisenaire rods look like. These are our Cuisenaire rods. Their values are: the white rod is 1, red rod is 2, light green is 3, pink is 4, yellow is 5, dark green is 6, black is 7, brown is 8, blue is 9, orange is 10. Alright, so you're going to start by taking your 6 rod and pulling it out. Now, your goal here is to make what we call these one color trains. Alright, so we want to make the lengths match, and we want to take our dark green rod and represent it in a different way using these one color trains. Alright, so of course you could use 6 of the white rods, but we're going to skip over that one. because we know that that's going to work for every single number. Every single Cuisenaire rod can be made up of multiples of the white rod. But we could use 3 red rods to match the length of that dark green rod. This would be representing the multiplication expression, the 2 rod times 3. You could also use 2 of your light green rods to match the length of that dark green rod. This would be matching the expression 3 times 2. So the 3 rod times 2. All right, so there's no other color that we could use to match the length. There's no other one color trains that we could use to match the length of that 6 rod. So now we're going to look at the 8 rod, which is our brown rod. We could use 4 of our red rods. All right, so again, that would be the multiplication expression 2 times 4. See, we can't use the 3 rod. We can't use that light green rod. We could use 2 of the pink rods. That would be the multiplication expression 4 times 2. The 4 rod times 2 times. And there's no other one color trains that we could use to match the length of that brown rod. So then you look at your little setups individually. All right, so let's take, and we're going to say, okay, we're going to look at our 6 rod, then we're going to look at our 8 rod and say, okay, do they have any one color trains that match? If they do, what's the largest color that matched? All right, so in this case, they both were able to be made up by these red rods, and so we can say that the greatest common factor of 6 and 8 must be that red rod, which is 2. Now we're going to use the intersection of sets method to find the greatest common factor of 75 and 45. This is not my particular favorite method. It involves writing out all of the factors of both numbers, and then you can either look at them as a set, or you can put them in a Venn diagram and see where they intersect. All right, so we're going to do the Venn diagram method this time, and then later on in the video I'll show you how to just do it with the sets written out by hand. All right, so you have one circle that represents the factors of 75, you have another circle that represents the factors of 45, and then of course you're going to have this overlapping part in the middle. So let me change to my pointer. All right, so you're going to have this overlapping part in the middle. That's where the common factors are going to go. All right, so remember, common factors, that's what we're looking for. All right, so the first thing you want to do is just list out all the factors of each number. So the factors of 75 are 75 times 1, 3 times 25, 5 times 15. The factors of 45 are 1 times 45, 3 times 15, 5 times 9. All right, so you're going to put the factors that they have in common in the middle. So they both have a 1 in common, they both have a 3 in common, they both have 5 in common, and 15 in common. All right, then the remaining factors are going to go over on the sides here. So the factors of 75 that remain are 25 and 75. The factors of 45 that remain that were not common were just 45. All right, so now you're going to look at the intersection. That's where those common factors are, and then you're just going to pick out the greatest value or the largest value that they have in common. All right, so the largest value that they have in common is 15. So, excuse me, I'm sorry, I missed a number there. 9 was supposed to go over there with the 45. But now we see that the greatest factor that they have in common is 15, so the greatest common factor is 15. Next, I'm going to show you how to find the greatest common factor in the format of a word problem. This is a problem that you may teach to your own students one day. It says, Rudy is making emergency preparedness kits to share with his friends. He has 15 bottles of water and 10 cans of food, which he would like to distribute equally among the kits with nothing left over. What is the greatest number of kits Rudy can make? All right, so a couple of things that tell me here that we're looking for the greatest common factor is that he wants to have nothing left over. All right, so the kits have to be able to be divided equally into these kits with no remainders. And like I said, the kits need to be divided up equally. All right, so we're really finding the greatest common factor here, but I want to show you how you can represent this visually. All right, so the question's asking, what is the greatest number of kits that Rudy can make? Well, the minimum number of kits that Rudy can make is 1. He could just put all of the water bottles in one kit and all of the cans of food in one kit. All right, so if nothing else, Rudy can put everything in one kit and share that with one friend. All right, but let's try to see if Rudy can share with more than one. So let's see if Rudy can share with 2 friends using the conditions that he set up for himself. All right, so what you're really looking at here is, can I split these water bottles up, or can I split these cans up evenly? All right, so I'm going to start divvying up the water bottles. I'm going to put 1 bottle in the first kit, 1 bottle in the second kit. I'm going to repeat this process over and over. All right, so now we have 2 in each kit, 2 waters in each kit. Now we have 3 waters in each kit. Waters in each kit, 5 waters in each kit, 6 waters in each kit, and then 7 waters in each kit. But here I run into a problem. I have a water bottle left over. If I put the water bottle in the first kit, that means that the water bottles are not going to be distributed equally among the kits. So this isn't going to work. I added in that sound effect just for you guys. Now that we know that Rudy cannot make 2 equally distributed kits, let's see if Rudy can make 3 emergency preparedness kits that meet his conditions, which are that the kits need to be distributed equally among, all the items must be distributed equally among the kits, and there should be nothing left over. All right, so hopefully what you've picked up on is that we're really dividing our items into the 3 groups, or into the 2 groups, whatever our number of kits is. We're dividing our emergency supplies into those kits. So we're going to take our 15 bottles of water and divide them up equally into our 3 kits. So that means that each kit is going to get 5 bottles of water. All right, now we want to take our 10 cans of food and split them up equally among the 3 kits. Now, you probably can already guess that this is not going to work, but let's watch what happens. So we're going to start distributing our cans of food. Each kit now has 1. Each kit now has 2 cans of food. Each kit now has 3 cans of food, but there's 1 can of food left over. So we know that this is not going to work. 3 kits does not work. Now, imagine what you would do if Rudy was making 4 kits. We would have 15 bottles of water that we try to split up into 4 groups. Is 15 divisible by 4? No, it is not. 15 is not divisible by 4. We would have bottles of water left over, and so we know that 4 groups would not work as well. But what about 5 groups? If we try to split Rudy's emergency preparedness items into these 5 kits, this should work, right? Because 15 is divisible by 5 and 10 is divisible by 5. So we take our 15 bottles of water, we're going to split them up into our 5 kits. That means each kit gets 3 bottles of water. Now we're going to split up our cans of food. All right, so since we have 10 cans of food, 10 divided by 5 is 2. That means each kit gets 2 cans of food. We have nothing left over, and so we know that this number of kits works. Rudy can make 5 emergency preparedness kits where all of the items are distributed equally among the kits and nothing is left over. Now think about what would happen if we tried to make 6 kits. 15 is not divisible by 6 and neither is 10, so that wouldn't work. If we had 7 kits, 15 is not divisible by 7 and it's not divisible by, and 10 is also not divisible by 7, so that's not going to work. So you would continue this on until you got to 10 cans of food, which again would not work. 10 is divisible by 10, but 15 is not divisible by 10. So 5 is the greatest number of kits that Rudy is able to make that meet his conditions of the food being distributed equally among the kits and nothing being left over. Now, what we've really done here is we have found the greatest common factor of 15 and 10. So let me show you the more formal way that we would solve this problem. We would say, okay, we're looking for the greatest common factor of 15 and 10, because that means that number would be divisible by both of those numbers with nothing left over. All right, so you would take, if we're using the prime factorization method, and we're going to do the prime factorization of 15. 15 can be split up into 5 times 3. Both of those are prime. 10 could be split up into 5 times 2. Both of those are prime. You look for the factor that they have in common. They both have a 5 in common, so our greatest common factor is 5. That tells us that the greatest number of kits that Rudy can make is 5. Now let's talk about the least common multiple, or the LCM. The least common multiple is defined as the smallest number that is a multiple of 2 or more numbers. All right, so before we were looking at the greatest common factor, this time we're looking at the least common multiple. All right, so it's got to be a multiple of both numbers, and we're looking for the smallest number that is a multiple of both of those, or more, both of those numbers, or all 3 of those numbers, or all 4 of those numbers, however many numbers we're looking at. There are many methods for finding the least common multiple of 2 or more numbers, among which include the number line method, the Cuisenaire rod method, the intersection of sets method, and the prime factorization method. The methods that I would like you to know for the exam are the Cuisenaire rods method and the prime factorization method. Let's start with the prime factorization method for finding the least common multiple. The prime factorization method for finding the least common multiple says, the least common multiple is the product of all of the primes in either number raised to the greatest power that shows up in either prime factorization. All right, so again, if you're looking at 2 numbers, suppose that you have their prime factorizations. Let's do a really easy example like we just saw with the emergency preparedness kits. We found that the numbers 15 and 10, their prime factorizations were 5 times 3 and 5 times 2. All right, so 15 is equal to 5 times 3. 10 is equal to 5 times 2. The least common multiple is the product of all of the primes in either number raised to the greatest power that shows up in either prime factorization. So for the least common multiple, we would include all of the numbers 5, 3, and 2. So 5 times 3 times 2. Then you would look at their exponents and say, okay, which one has the highest exponent? These all have an exponent of 1, so we don't have to worry about that here. But if we had something that was like 5 squared times 3, then we would put the squared on the 5. All right, so you include the greatest power that shows up in either prime factorization. All right, so for the numbers 15 and 10, the least common multiple would be 5 times 3 is 15, times 2 is 30. Let's use the prime factorization method to find the least common multiple of 8, 56, and 64. We're going to start by finding the prime factorization of all of the numbers. 8 can be broken down into 4 times 2. Its prime can be broken down further into 2 times 2. So now we've got 8 broken up into the product of primes. It's 2 times 2 times 2. Now we do the same for 56. 56 can be split up into 8 times 7. 8 gets split up into 4 times 2. 4 gets split up further into 2 times 2. So now we have a product of primes, 2 times 2 times 2 times 7. And now 64. 64 can be split up into 8 times 8. Your 8s can be further split up into 4 times 2. 4 can be further split up into 2 times 2. We do the same for the other 8. Split up into 4 times 2. 4 gets split up into 2 times 2. Now we have a product of primes, 2 times 2 times 2 times 2 times 2 times 2. Oh, I'm missing one of my circles. There we go. Now we know from our definition from the last slide, the least common multiple is going to be the product of all of the primes in either number, raised to the greatest power that shows up in either prime factorization. All right, so let's go ahead and write out our prime factorizations. Now we're going to look at what they have. We're going to list out all of the primes that are in either number. So recall the prime factorization method tells us that the least common multiple is the product of all of the primes in either number, raised to the greatest power that shows up in either prime factorization. So our least common multiple is going to include the number 2, and it's going to include the number 7. Now we look at the number 2. What is the greatest power that 2 is being raised to in any of these prime factorizations? 5, right? So it's going to be 2 to the 5th times 7. 2 to the 5th times 7 is 224, which is our least common multiple. Now that we have a pretty solid understanding of how we can use the prime factorization method to find the least common multiple, we're going to look at how we can use Cuisenaire rods to find the least common multiple. This would be a great activity for younger students and is a really great way that they can use manipulatives for finding something that is traditionally something that students struggle with. So the Cuisenaire rod method for finding the least common multiple says that the least common multiple is found by building one-colored trains of each number until the trains have equal length. All right, so let's look at an example. Let's use Cuisenaire rod to find the least common multiple of 6 and 8. All right, so just to remind you, these are our Cuisenaire rods. I'm going to quickly write down their values. Okay. So we're going to start by looking at our 6 rod, our dark green rod, and then underneath it we're going to put our 8 rod, our brown rod. Now we're going to continue building these one-color trains, so we're going to continue adding 6 rods and continue adding 8 rods until these trains have the same length. Alright, so we add another green, then add another brown, add another green, add another brown, add another green, and we've reached the same length. Alright, so now you just want to add up the rods and figure out what length they now have. Alright, so if you have 4 of your 6 rods, what is the length of that train? If you have 4 of your 6 rods, 4 of our 6 rods would be 24. And 3 of our 8 rods would also be 24. So our least common multiple is 24. Now I want to show you the intersection of sets method for finding the least common multiple. Using this method, the least common multiple is found by listing all of the sets of, by listing the set of all of the multiples of each number, and then finding the intersection of these sets to find the common multiples. Now I've put quotation marks around the word all here because multiples go on forever. You can't list all of the multiples of each number, but you're going to kind of list them until, list the first 8 or list the first 10 of the multiples, and then you're going to find the intersection of these sets to find the common multiples. The smallest element of the intersection is the least common multiple. All right, so remember, with the greatest common factor, we were picking out the greatest factor that they had in common. This time we're looking at the smallest number that is in the intersection of those sets. All right, so you're going to start by listing out the multiples of 28 and 36. The multiples of 28 include 28. 28 times 2 is 56, times 3 is 84, times 4 is 112, times 5 is 140, times 6 is 168, times 7 is 196, times 8 is 224, and times 9 is 252. So I've listed out the first 9 here. If we look at the multiples of 36, we have 36, 72, right, again, so that's times 1, times 2, 103 is times 3, excuse me, I said that wrong, 108 is times 3, 144 is times 4, 36 times 5 is 180, 36 times 6 is 216, and then 36 times 7 is 252. So you only need to list these multiples until you find that common multiple, remember, because it's supposed to be the smallest multiple that they have in common. So since 252 is a member of each of these sets, we know that it must be the least common multiple. Now let's look at an example of the least common multiple in a word problem. Suppose that we have 3 motorcyclists that ride around a circular course starting at the same place and the same time. The first passes the starting point every 12 minutes, the second passes the starting point every 18 minutes, and the third passes the starting point every 16 minutes. So the first motorcyclist is the fastest, the second is the slowest, and then the third motorcyclist is in the middle. After how many minutes will all 3 pass the starting point at the exact same time? So what we're looking for here is the least common multiple of our motorcyclist time. So we start by making our prime factorization. We take 12, break it down into its prime factorization. It's 2 times 2 times 3. 18, break it into its prime factorization. That's 3 times 3 times 2. 16 gets broken down into 2 times 2 times 2 times 2. Then we're going to write out their prime factorizations. And remember, the rule for finding the prime factors, finding the least common multiple using the prime factorization method says you want to include every prime that's in any of your prime factorizations. So we're going to do 2 and 3, and you want to raise that to the highest exponent. Right, so it's going to be 2 to the 4th times 3 squared, which is 144. So after 144 minutes, all of our motorcyclists will pass the starting